So yeah, what I'm presenting today is really just more of a thought exercise than a scientific study. Like I said, we just passed the year 1 mark on a 3-year project. The Deepen project, others from the project have presented earlier this week. Eric Sonnenthal talked about reactive transport modeling of supercritical fluids. Pat Dobson talked about conceptual models for magma-driven geothermal systems. And then Andre Stephenson talked about geochemical modeling and signals of supercritical fluids. And then later today, you'll hear a presentation from the project leads from Reykjavik Energy, Vala and Gunnar, on Deepen's major objective of targeting the IDDP3 well. And so my institution's part in this project is really focused on understanding the challenges in exploring for superhot resources. Here's how I've organized today's talk. I'll give a little background on exploration methods in general for geothermal systems, and then what we're drawing from to explore for multiple plays in magmatic settings. We'll be focused on training site development as part of that multi-play fairway analysis method I'll talk more about. Then I'll talk about how we're characterizing these multiple plays in magmatic systems, and finally present sort of our preliminary thoughts on developing a 3-dimensional play fairway analysis framework for multiple plays in magmatic systems. So Deepen stands for de-risking exploration of geothermal plays in magmatic environments. And so, you know, I talked about exploration challenges. You know, the challenge that we're particularly concerned with in the US is not just what are supercritical fluids, but where do they occur? So, you know, there's been a lot of talks talking about the requisite conditions for supercritical fluids, what are the characteristics of the actual fluids themselves, and then, you know, what is the degree of magmatic gas input, what is the relationship to maybe exploitable resources in terms of superheated steam. But the question we were sort of stepping back and asking was, you know, are supercritical resources or even super hot systems more broadly defined really confined just to the roots of hydrothermal systems, or might they actually be in different settings altogether? And exploring through training sites, what is their likelihood of occurrence based on tectonic settings, structural features, magma type, reservoir rock type, and other parameters. You know, most countries in the world, like the US, have completely different magmatic, you know, volcanic or plutonic settings than those that have been drilled in Iceland, for example. And some of those are developed, and then there's lots of volcanic and plutonic settings where development of conventional hydrothermal is less favorable, such as continental arc systems that might not host large volumes of exploitable hydrothermal fluids, but could they be candidates for super hot resources, whether it's EGS or actually supercritical fluids that are being exploited? You know, so the main question we're asking is, do supercritical resources or super hot resources form under the same geological conditions as exploitable hydrothermal systems in magmatic settings? And then, you know, once we've started down that road, then how do we explore for them? So we've talked about some geochemical signals and methods that these systems might produce at the surface or in wells. We talked a little less about the geophysical signals and methods. That's something that our Deepen team is really focused on, particularly in Iceland. And then there's this whole picture approach, which Pat touched on when he went through the different conceptual models, you know, and then, you know, that's about integrating multiple data sets as well as this 3-dimensional play fairway analysis method that I'm going to talk about more. So a bit of background on the play fairway analysis method. It was a method developed by the hydrocarbon industry to assess exploration risk from regional to prospect level scales. So more recently, it's been applied to geothermal exploration, and really the focus is on finding blind resources. You know, supercritical, super hot resources, I think, fall into that category as blind. So we thought that the PFA approach is pretty applicable. The approach involves compiling and synthesizing data that indicate the presence of an exploitable resource at depth, and then categorizing, weighting, and combine the different data sets. So typically, with this play fairway analysis approach, you develop a set of training sites to determine the categories and weights of the data types, and then you combine those weighted data types with direct evidence to produce a fairway. And the fairway is a spatial distribution of the geothermal resource favorability. again, the whole point is to limit exploration risk for blind resources. And so over on the right, you see kind of a cartoon of what outputs look like, where they're generally limited to the compilation of surface data for unexplored or green fields. And so they result typically in two-dimensional favorability maps, also called composite risk segment maps. So for geothermal resources, the typical hydrothermal play has been divided into three basic components: heat, fluid, and permeability. Some of those apply to supercritical and superhot. Some of them might need to be tweaked a little bit. And each of those particular components then is assigned high, moderate, or risk or low risk levels, and then combined into a composite risk segment map to show the favorability of geothermal resources. So that's sort of the general approach. There were, for those of you that don't know, over the past decade, the United States Department of Energy has supported 11 geothermal play fairway analysis projects in the US. 5 of those projects were in magmatic settings. So upper right shows the PFA project in the Hawaiian Islands. And the colors there are the probability for geothermal resources, also referred to as favorability. So warmer colors being more favorable for hydrothermal resources. And that shows all of the Hawaiian Islands. On the lower right is the Washington State play fairway analysis that was done, and it was restricted just to the volcanic belt known as the Cascade Range. And again, warmer colors indicate higher favorability. On the left, we see the favorability outcomes for the study that was done in the Central Cascades. And then there were also studies done in the Snake River Plain, which is the Yellowstone hotspot trace in Idaho. And also there was a study done in the Aleutian Cascade volcanic belt of Alaska. Our deepen approach, like I said, it sort of draws from this model, but it takes a different approach. So first difference is that we are not looking just for hydrothermal plays, right? We are considering multiple plays. We're not discounting hydrothermal, but we're also looking at superhot plays, which we consider to be superhot EGS plays and then supercritical fluid plays. So those are our 3 play types that we've developed right now. And then, our workflow space is in the 3D, not in the 2D space. So basically we're adding in the vertical element as the fairway. And then obviously, to look for superhot and supercritical resources, we are integrating the processes occurring at the root zone of hydrothermal systems, and at that magmatic interface and the brittle ductile transition zone. So what we're trying to do is develop outputs that are favorability volumes in 3D space, and again, for multiple plate types. So shown on the left is just a schematic from a paper by Pu and O'Brien 2020, which shows what a favorability index might look like for 3D play fairway analysis. Okay, so most of the work over the past year that NREL has done has been focused on developing training sites. Again, with these 3 different play types in mind. Pat went through this a little bit, but we have 14 worldwide training sites. So there's 8 in the United States. I'll go into those a little bit more in a minute. And then there's 6 international sites, with all of which you all are very familiar with, more so than we are. The project also has 2 application sites where we're going to be applying the play fairway analysis methodology to exploration for on one site, it's a superhot EGS business model, and the other site, which is the site of IDDB3, it's a supercritical well at Hango. Here's just a quick overview of all of the training sites we've developed data, we've compiled data for. So like I said, we've got 8 in the United States, 5 of which were those 5 magmatic play fairway analysis projects I referred to earlier. Those are all, for the most part, undeveloped fields, or they might have 1 developed system in a large region. Those are typically in subduction-related settings, arc settings, volcanic settings. Well, I should say 3 out of those 5 are in those types of settings. The Hawaii and the Snake River Plain projects, like I said, are in hotspot settings. One is a continental, the other is a oceanic. One of the reasons we selected those sites was also just because there's, a vast amount of publicly available exploration data through the geothermal data repository that USDOE hosts. We also selected 3 others in the United States for different reasons. We selected Newberry Volcano. Like I said, that's one of their application sites for this methodology. Newberry Volcano was the subject of Eric Sonnenthal's talk. It's a pretty interesting magmatic and tectonic setting, and it's supported by some of our industrial partners. And then we also selected COSO and the geysers, which are very well developed geothermal fields that are in totally different tectonic and volcanic settings than the Icelandic and Japanese and Italian site work that's been done. So I won't go too much into the international training sites because all about those. But this is the full list. What we've been doing is collecting, all of the data we can from these sites, and there's a lot of it. The common data types are listed here. I'm sure you're all very familiar with what those are and what they do. There's also actually a list of less common data types that were collected, sometimes in very site-specific, for very site-specific reasons. So we collected all of those for the 14 sites, and we've been compiling them in a 3D modeling environment called Leapfrog Geothermal. Here's just 2 examples, one of an undeveloped field and on the right of a developed field. So this example shows what our 3D compilation looks like, where you combine 2D data. Here it's a geologic map, including rifts and faults. We've got geodetic data in there. We've got actually you can't really see very well the other layers because the geologic map overprints them, but we've got magnetics, gravity in the 2D layer, as well as points for geochemical sampling. And then you can see that, the 3D data, it basically just includes seismic and very limited well data. And then for a developed field, we actually took out some of the well data here so you could see better. The developed field snapshot it really just shows the different 2D and 3D layers that would include also, for example, a thermal model. In this case, you see some temperature isosurfaces. We also, in the background there is a resistivity model, etc. So like I said, we've been doing this for 14 sites, and the point of it is kind of twofold. The first point is, to be able to develop weightings for a play fairway analysis approach, and that's what we've been focused on. But the second point that really we're just starting work on is to be able to query some of these data for for sort of cross-site analyses. So here's an example, it's very preliminary, of a kind of comparative analysis we can do with some of the training site data we've compiled. Here we just looked at seismic event density as a first order estimation for the depth of the brittle ductile transition zone in 8 out of the 14 sites that we had good data for. And so what we did was we developed this sort of histogram approach where we projected all of the seismic events onto one plane, and then we took the probabilistic density for all of those earthquakes, essentially, for the 8 training sites to try to see if there was a maxima that would correspond to a brittle ductile transition zone boundary. So I'm just showing you a snapshot of preliminary results. We have a lot of work to do in terms of cleaning up the data, but this is just the kind of thing that we're going to be doing as part of this project over the next couple of years, and hoping to work with some of the groups actually on this call on. So back to the play fairway analysis approach we're taking. Clearly we all, well, I wouldn't say we fully understand hydrothermal plays in magmatic systems, but we sure understand them better than the other types of plays. And so, you're probably familiar with this model that was cited in the Melkenal geothermal play type paper. Here's one vision of the type of thing we're going to be exploring for in hydrothermal systems related to magnetic, in this case, a volcanic center. I won't go into this too much. Really, the question is, how do we understand supercritical plays? And so one of the ways we tried to understand supercritical plays was to read a lot of papers by the authors, presenting in this symposium. So we won't go into that too much. That would be boring for you guys, but we kind of took a similar approach to Thomas Dreisner earlier, where we looked at ore deposits as analogs. Obviously, they're exhumed fossil systems, and we can sort of, see into the supercritical part of these systems that we haven't drilled into for active systems. And we kind of had some very similar takeaways to Thomas that he presented earlier. So, these systems are characterized by this overlying zone of transiently ascending magmatic hydrothermal fluids. And then, that tends to breach the ductile rock boundary at temperatures between anywhere from 400 to 700 degrees Celsius, depending on rock type and strain. And then this upper brittle zone, as we all know, is characterized by non-magmatic and magmatic fluids under hydrostatic pressure. High fracture permeability is pretty typical of, these systems above, below 400 C. And then again, as Thomas pointed out, the fracture permeability is lower above around 400 C, depending on rock composition, magma composition. But as Thomas pointed out, at high stray range, rock will undergo brittle failure and hydrofracture. And so the question is, where in the world can we find these high strain rates? Are we just looking for high strain rates that are associated with ascending magma or magmatic hydrothermal fluids, or both? Or are we looking for high strain rates from tectonic strain, or if there's some kind of Goldilocks situation where both of these are happening, worldwide and in specific settings? The other takeaway from looking at ore deposits is that phase stabilities and then the resulting critical curve is really a function not of pressure and temperature only, but also of salinity of composition. And as you all know very intimately, the supercritical fluids can really form in both high pressure, temperature, and high salinity conditions, as well as low PTX conditions. And clearly, for exploitation, we prefer to target these low PTX conditions. So where do those occur? So what does this mean in terms of exploration? So some of the signals and clues, we've come up with so far won't surprise you in terms of, that we really need to understand the signals from transient complex systems in dynamic magmatic environments. So we really are looking for this Goldilocks environment of the right strain and the right temperatures, and potentially even the right magmatic or host rock compositions to allow for brittle, behaviors at the temperatures we need. Again, the supercritical fluid regime is not defined just with reference to temperature and pressure for binary or multi-component fluid systems. So, a lot of these ore deposits papers show that almost every supercritical system is unique based on the interplay of pressure, temperature, and salinity or compositional conditions. And so a range of potential fluids might be contained in any given supercritical geothermal reservoir. So some signals that can be captured to guide exploration are, geophysical signals related to steep chemical and physical gradients driven by these dynamic conditions, pressure, temperature, and composition. So such as things like contrasts in magnetic resistivity and gravity, those can be interpreted as structural boundaries or transitions between zoned alteration and mineralization. Patterns of demagnetization, so things, especially in dikes and structure, maybe pyrite mineralization, are useful for constraining the mineralizing system. We haven't talked too much about, the need to constrain these fluids, but both the ore deposits literature and some of the process modeling seems to require that. And then, in terms of resistivity signals, we're looking for resistivity lows, again, associated with alteration, but also, the argillic alteration that Pat mentioned as a key component of some of the conceptual models, but also the occurrence of sulfide minerals as indicators. Electromagnetic methods can also help with structure and, distinguishing between magma, rock, and fluid in the subsurface. Some other signals related to silica content could be sought out using resistivity and gravity highs. And then lastly, we could use the gravity contrast between intrusions and country rock to help define the boundaries of depth. When it comes to superhot EGS, actually we can draw pretty well from classic EGS conceptualizations, where this figure comes from Beardsmeer and Cooper's work in Australia, exploring for EGS resources, but not necessarily super hot ones. But our, at Newberry EGS site, for example, the developer is going with a similar model where you have a heat source component, a fluid component, but obviously the fluid is, not a native fluid, but we're concerned about the interactions between injected fluids and host rock. And then we're concerned with an insulation feature, and we're concerned with the particular, reservoir features that would sustain production over time, such as stress state and the depth to the brittle ductile transition zone. So what this all means is that, when it comes to conventional hydrothermal plays, like I said, the play fairway analysis framework relies on the key components of heat source, fluid, and permeability. Exploration for those three components is not perfect, but it's, there are conventions around this. And so, we were able to rank the methods based on our play fairway analysis kind of review of previous work. And so here are just some of the rankings we came up with. And those will be translated into numerical weights for the play fairway analysis that we'll be doing. When it comes to superhot EGS, this, we're having to sort of develop the framework for it. So here's the exploration methods that are, sort of ranked by priority, but not necessarily numerically ranked. Like I said, we have a heat flow component for superhot EGS. We have an insulation component. We've got a reservoir component, and then a fluid component that's, related to the injectate. And then when it comes to the framework for supercritical plays, like I said, this is in progress, but, we really have to look at the heat source as kind of two components rather than just simplifying it into conductively heated rocks. We can draw from that, but we also have to really look into dynamics of, magmatic bodies. And then for the insulation and seal component, I think we still need to integrate some of the reactive transport models and a couple process models here, but we're, considering the thermal conductivity of the overburden as well as alteration mineralogy seals or caps. When it comes to the reservoir potential of supercritical, or the potential for supercritical reservoirs, we're going to be mostly looking at the same types of data for the permeability part, but then we're also going to be really focused on that brittle ductile transition zone, like Thomas was talking to earlier. And then I would say, in terms of building out a framework around characterizing fluids, we really need to keep our eye on all of these geochemical models that are coming out of the projects being discussed here, and also some experimental work to define chemical and isotopic characteristics of supercritical fluids, and then compare those to sampled fluids from wells and other sources. That's all I had. Thank you.
Thank you, Amanda. That's brilliant. Yeah, I've got some echo here. I just want to say, do we have any questions? No, we don't have any questions for you in the chat that I can see, but I would like to ask a quick question myself. It's about this concept of the benefits of a training model, and I wonder whether you think artificial intelligence, getting a computer to do this for you with a database, with a sufficiently populated database, might be worth doing, given that you have already admitted that these systems are very complicated and in many ways unique. So is there enough similarity between different play types, if you like, that would benefit from this approach of sort of an artificial intelligence approach that has been very popularized recently?
Right. That's a really good question. I think, we do have a lot of surface data for these 14 sites. We have shockingly low amounts of subsurface data for most of the sites. So I think, considering that considering the tremendous degrees of uncertainty between projecting from 2D surface data into 3D subsurface data, I wasn't always convinced of the value of artificial intelligence for this particular approach. Having said that, the United States Geological Survey right now is going through the 11 PFA sites. So the 5 magmatic systems I discussed were only 5 out of 11 sites that were candidates for the plate fairway analysis kind of exploration approach. So the USGS is going to be doing work over the next couple of years applying machine learning to those 2-dimensional approaches for plate fairway analysis. And we're actually meeting with them later today, or no, it's tomorrow, to talk about potential ways to think about it for the 3D space, considering the scarcity of our 3D data. But that's absolutely a really good point, and I think that's something we need to always be keeping in mind.
Okay, great. And just very quickly, a question from Pat. Given that we don't have operational supercritical systems, how would you propose how different data inputs are weighted for the PFA? Another tricky question.
Yeah, we're working on it.